Okay, then hello everyone. My name is Alexandru Militaru. I'm a master's student at University Polytechnica of Bucharest, and I'm in my last year of studies. I also work as a consultant for Symmetry Investments and use D in my daily work. Thank you for inviting me and for your interest in our work. Today I'm going to tell you how we at Symmetry Investments use Cling and cppyy to call C++ libraries from our in-house developed domain-specific language, which is called seal and is written in D. The key component here is a seal plugin, which is also written in D and is called the seal Cling. Which allows us to interact with cppyy from seal. seal stands for Symmetry Integration Language. As I've said, it's a D-based domain-specific language of functional flavor. The idea was that we needed a language that could bring the whole company together under the same semantics and the same process definition language. To solve this problem, the language had to be designed from the ground up to be easily interoperable with other systems and languages. So we decided to implement it in D, which is a very plastic language and provides a static reflection mechanism that can be very useful for this kind of interoperability that we needed. One of the languages that we needed interoperability with was C++. That's because Symmetry is an investment management company, and many of the market data APIs that we need to call are written in C++. Of course, we didn't want a different C++ project for each API that we wanted to call, because that would imply having someone who maintain those projects. And more than that, our practitioners are not programmers, so it's easier for them to write seal instead of C++. So what we've done was to create a plugin for seal, and this plugin allows us to call C++ libraries. Seal Cling is like a middle ground between seal and cppyy. It interfaces with seal through the static reflection mechanism. I'll give more details about this a bit later. And it interfaces with cppyy through the C API that the latter provides. For the moment, our main dependency is the root project. That means we do not build cppyy and Cling outside root. We know that might be possible, but we didn't spend time trying to make it work that way. In fact, what we've done was to settle for a specific root commit, and we created a fork, but we also keep an eye on cppyy master for bug fixes. Anyway, I think that the cppyy version from the root project is slightly different from the cppyy master, so I think it's worth keeping an eye on both to see what improvements are made. Just to give you an idea, at the moment, Seal Cling has about 2.5 thousand lines of code, and it's growing. And now let's have a more detailed look at how Seal Cling interfaces with seal and cppyy. To be able to interface with cppyy, all we have to do is to include cppyy's C API header in our code, run dpp, which is a tool that allows you to include C headers in your D code, link in the shell library of cppyy backend, and that's all. Then we can use it. Here is what it looks like. You have to create a .dpp file, then include the C header that you need, and then just write a D code that uses that C header. Here we have a D wrapper for a resolve name, which just calls cppyy resolve name, gets the result, creates a duplicate, and then frees the memory. Once we've written this file, we have to run dpp that will generate the D source file that we use to build our plugin. One of the patterns that we used a lot was to use cling to compile, to write and compile C++ helper functions. For example, here we needed a way to call add include path, which is an interpreter function that lets you add paths to the header files of the libraries that you want to call, but we didn't find a function in cppyy that lets you do that. So we created our own wrapper and compiled it using cling. We do this inside a module constructor, a constructor that it's executed before the main function starts. And this is how the D wrapper for add include path looks like. The first thing that we have to do is to create a scope object with the name of the type, cling D statics. Scope, it's a class that wraps cppyy scope T and all the cppyy functions that provide reflection information about functions, data members, enums for a given namespace, class, or struct. Once we have this scope object, we can create an object of cling D statics. To do that, we use a class called class. This class wraps cppyy object T and all the cppyy functions that have to do with memory management. Once we have an object of this kind, we use our scope object to get the handler of the cppyy method that we compiled. So we just call cppyy get method and get the method handler. And once we have the object and the method, we call this template function from here, which calls the appropriate cppyy call function depending on the template parameter that it receives. Here in this example, it receives a void because add include path returns a void. It doesn't return anything. In what regards the interface with CIL, we expose from CIL-cling wrappers of C++ entities through this static reflection mechanism. In order to expose the relevant types and functions, all we have to do is to call some template functions that CIL provides. And once we pass the relevant types and functions through those template functions, CIL is able, using the D-static reflection, is able to understand the structure and their properties. And in this way, CIL is able to communicate with CIL-cling. In fact, we expose two core types. One is a CPP namespace, which is a wrapper for a C++ namespace that allows free function calling, access to the namespace's variables, and object instantiation for the classes that are defined inside that namespace. And the other type, it's cling object, which is in fact a proxy for a C++ object, which allows method calling and data member manipulation. Given the fact that cppyy represents namespaces, structs, and classes as scopes, and any reflection information about this is provided through its associated scope object. Our wrapper types have a data member that holds a reference to their associated scope object from cppyy, and this object is queried whenever we need reflection information about these entities. All the calls that are done through these two wrapper types that we expose to seal, CPP namespace and cling object, are done through the same interface, this one, which is a template function that receives a wrapper object, a function name, and a sequence of arguments. This is like the starting point of the calling procedure, a procedure which can be divided into three separate phases. The first one is the overload resolution, the second one is the argument conversion, and the last one is the actual calling. By overload resolution, I mean that for a given object or namespace, we fetch all the method overloads for a given function name, and we try to figure out which one the user is trying to call. In order to do that, we test two things. The first one, that the method overload has the right number of arguments equal with the number of arguments that the user provided. And the second thing that we test is that each seal variable provided by the user has a valid type conversion to its corresponding parameter from the overload which is tested. In order to find the match, we do two iterations. In the first iteration, we only allow exact conversions, like from a seal long variable to a C++ long. And in the second iteration, we allow lossy conversions too. By lossy, I mean conversions that allow a loss of precision or range, like from a seal long variable to a C++ int or short. The argument conversion depends on what lies behind the seal variables provided by the user. In seal, everything is wrapped in a variable, so we have to distinguish between seal primitive types and cling objects. If if a parameter provided by the user it's in fact a cling object, then we do a set of string comparisons between the type of the C++ object that is wrapped in that cling object and the type of the overloads parameter. But if we have a seal primitive type, then it must match one of the predefined type coercion rules. A type coercion rule looks like this. It is a structure with three fields. The first field, it's the name of the target type. In our example, a char pointer. And the other two fields are delegates. This is a concept that has to do with function pointers. The first delegate can coerce. It's the actual rule of coercion, a lambda function that tests that the argument provided by the user has a type of string, and the coerce delegate, it's the actual coercion, the lambda function that does the actual coercion, meaning that in our example, it extracts the string from the variable provided by the user, it converts it to a char pointer, and then wraps it in a way that's suitable for cling. Once the argument conversion is done, we can perform the actual calling. This is done by examining the return type of the selected overload and trying to figure out which seal type the C++ return type of the overload, and trying to figure out to what CIL type the C++ return type should it be converted. So we have to distinguish between return types that are C++ primitive types, between types that should be wrapped as Cling objects, and types that are just not supported yet. For example, if we have to do with C++ primitive types, then we have a switch over a hard-coded list of primitive types, and we just call the appropriate function, the appropriate cppyy function. However, to distinguish the return types that should be wrapped as Cling objects, what we do is to try to find the scope resolution operator in the name of the return type. By this, I mean that we try to see if the type comes from a namespace. I know it's not the best assumption, but it works in practice. And for the types that are just not supported yet, we have an assert which let us know about that. In what regards the data members, it is access to them, it is fairly straightforward because it involves an offset calculation. Here we have a function that sets a data member of a primitive type. It receives a wrapper object, the data member that must be set, and the actual data. We take here the offset of the data member, and if it's not, if the data member is not owned by a Cling object, then we just set the pointer. If it's owned by a Cling object, then we have to compute its address by also adding the address of the Cling object pointer and the offset. We are continuously improving our plugin, and one of the things that we would like to add in the future would be automatic instantiation of templates. For example, here, to be able to call just ret, we first have to instantiate this template by hand, and it would be very useful for our users to have CIL-Cling do this for them. And another thing that we plan to add are direct conversions to and from CIL arrays, which are heavily used in our language, and std vector. As a summary, CIL-Cling is a CIL plugin that allows transparent calling of C++ libraries. It is built using Cling and cppyy, and at the moment it allows us to call various C++ libraries like Boost ASIO, dlib, Zapian, PDFtron, and others. I'll give you some examples in the demo session. Thank you very much for your attention.
Thank you, Alessandro. This is really impressive. Does anybody have questions before we move to the demo? We can probably ask the questions afterwards.
Yeah.
I have maybe one question. So the way that the cAPI was grown was purely organically. I think we explained that once also to you in over in one of the bug reports or whatever. It would be very nice if some of the shortcomings that you mentioned over here were listed and handed off to the Fazil and friends, so that the next iteration of lib-interop doesn't make the same mistake. Some mistakes, like I said, it was just whatever I needed. I created an API call rather than thinking, oh, this is the best way of doing things. And now having multiple implementations means that we should have a better idea of what is the way it's actually supposed to be done, rather than looking at how it was done historically.
Okay, sure. Most of the problems that we had were with enums, but I also posted some questions on on cppyy master, I guess I've discussed with you.
Yes.
But I also have some things that must be resolved, and I will create some issues.
Yeah, that would be not just to me, but to Fazil for the design of libinterop. I mean, there's some things in the CAPI just silly, where you have functions that are very similar, but then they take different arguments. One takes the type handle, the other one goes by string, and etc. etc. That's kind of silly. Another thing that is very inefficient is the way that that lookups work. Again, this was done for my own convenience from Python, and this may not be the same for you. So you might get inefficiencies under the hood, even though you may not see it in functional terms. It would be nice to figure those out too. For the next iteration.
Sure. We can discuss about these shortages and maybe give you some advices in this.
Thanks.
Okay. Thank you.
More questions? Okay, I have one. So you mentioned that I will start in a different way. I'll shoot my second question first. So did you do performance studies on where the bottlenecks are in the integration layer? Because in the end, you have this layer which kind of translates and goes back and forth with strings and things like that. Do you have an understanding what's the bottleneck?
No, at the moment, no, because we don't have that much libraries that we call. So the libraries that we can call at the moment, I think they work pretty well. So we didn't need those performance statistics. But if you are interested, I can do them and discuss after.
Yeah, I mean, if you are happy with what it is, I think it's good enough feedback for me. That means that there are no obvious performance bottlenecks. But it would be good if you have that. It would be good for us to figure out what needs optimizing. And the other thing that I was about to ask is, what is missing? What you like from what you have used, and what you would like to have? What would make your life easier if it was there?
Let me think for a moment. It would be interested to have more functions that provide reflection information about templates. For example, more about their constraints, their parameters, their types, and so on.
Yeah, I fully agree. Fazil, that one is on you. I fully agree.
Yeah.
I've never heard about that request. I'm kidding.
I see. Yeah, I mean, most of the C++ libraries that we need to call are full of templates, and as I've shown you, I have to do this by hand. I have to create some helper functions in C++, and that's a bottleneck for performance also. But performance, it's not that important for us, but it's the work as such, because I have to create this let's say stubs in which I instantiate templates by hand, and having more reflection information about templates would help me with would also help me implementing automatic instantiation. But I think cppyy has that. Am I correct?
Not efficiently, and the other problem is there's a lot of trial and error to find where you need to go. So yes, you can do it, but like you say, it's a lot of work on your end to find all the possible options. and it's inefficient.
Yeah.
Very inefficient. So
Yeah,
we tried binding very large template libraries. I mean, think about PCL, Eigen, that kind of stuff, and it's dreadful.
Yeah, I understand.
Yeah, I'm actually surprised that this even leaks out of cppyy, because I think the biggest issue here is that currently Kling or whatever interface we look at doesn't provide sort of an enumeration of options, template parameters and whatnot. And much of that is actually handled already by cppyy. So you are absolutely right, Alexandru, and it's even more so than what you see using cppyy.
Okay.
Okay, thank you. More questions? If not, let's jump to the demo.
Sure. Can you see my screen?
Yes, I can.
Okay, so in the first example, we call dlib. It's a C++ library that has some that provides some machine learning algorithms. What we do here, it's we load the shell library of dlib. We include a helper header because I had to wrote some helper functions. Here I get a wrapper of the dlib namespace. I get the face detector using this wrapper, and I create an image matrix. Then I also get a wrapper for my helper namespace. And using this wrapper, I load the image. I make the image bigger by a factor of 2 because this is useful for the algorithm. And then just apply the face detection algorithm and save the image with this name detected.jpg. Let's see how it works. We have this image of Tom Cruise, and then okay, we run the script. It takes a bit to run. I think it's because the algorithm, and we have this detected.jpg, and the algorithm successfully detected the face of Tom Cruise, so it works. The second example, in the second example, we call Zapier, which is a search engine, open source search engine written in C++. Here we have the indexer script. We also load the shell library, include a header, get a wrapper of the Zapier namespace, and we use that wrapper to create a database. And here I wrote a small function that takes a content and a list of keywords and creates a document with that content, and also adds the keywords, and then adds the document to the database. And I've called this function 3 times with this proverbs and these keywords. And here we have the indexer, the querier script, also loaded the shell library, included the headers. Here I wrote a helper function to print the matches, the search results. I get a handler of a CPP namespace. I open the database, start an inquire session. And here I also wrote a small function to run the query. It receives a word and creates a query, sets it in the inquire session, gets the top 10 results, and then I use that helper function to to display the search results. And I call the function with 4 words: people, Johnny, gift, and door. Let's see how it runs. First, let's remove this database, and let's call the index search script. Once it runs, a database is created. And now if we run the query script, there are 4 queries, first with people, and we got two results here and here. For Johnny, we get only 1. For gift, also 1, and for door, 0 results because there is no sentence with this word in it. So this works too. And our last example, it's a small client server app using Boost ASIO. Here we have the server. I wrote some helper functions. Here I get some wrappers of Boost ASIO namespace and this TCP namespace, and also a wrapper for my own namespace. I create a service and the name endpoint. Here I create an acceptor socket for listening on the incoming connections. Then I create an active socket for communication with the client. Then I use the accept function to wait for connections and then use the active socket to communicate with the client. Here I wait for a message, and when it comes, I print it and then send a reply where I add hello to the message. And here I have the client. I create a service, an endpoint, created a socket, and connects to the endpoint and sends this message with demo, and then prints the message that I received from the server. Let's first run the server. And now let's run the client. So the client sent demo to the server received demo, and it sent back to the client hello demo, and the client received the message from the server. This was the last example. If you have any other questions, we'd like to hear them.
Thank you. Very nice. Questions or comments? So I had a question. The way that you operate on SIL is that you kind of create these clink objects, and once you kind of resolve the namespace or the concrete thing, then I saw you kind of then use them to call. Is that the model that you use, or I am not understanding something?
I don't think that I understand the module, the way that are you talking about. Can you repeat?
So you make a like a lookup. If in one of your examples you kind of curate ASIO or something like that, and then I saw it got assigned to some object, and then in this, do you call methods of this object? Does that object like wrap the properties of the C++ entity?
No, I mean yes, I do. Once I'm trying to call a method. That method, I try to search that the name of the method. I try to search it using cppyy, and if I discover that there's a method, at least one method overload, I try to check if the arguments are correct. And if there's no overload for that, I throw an exception.
And that's happening behind the scenes because we did not see that in the example.
Yes,
okay.
yes.
Okay,
Yes.
got it.
Yeah, there's a layer Seal gives to the plugin. Well, someone tried to call this method, and I take the name of the method. I also receive from Seal the object on which that method is called, and I try to see what's the type of that object, and does that type provide a method overload with the name of the function which user called, and then I try to solve the call by calling cppyy functions.
Okay, thank you. Unless there are any other questions, I would like to thank Alexandru. Thanks a lot, and you're welcome to join anytime that you want to understand about new things that we're doing. And one of the things that we will be doing is this language interoperability layer, where I think may be useful for you. It will be modeled by learning our lesson from some of the things that Wim pointed out. But your feedback is welcome and highly appreciated.
Sure, thank you very much. Thanks for invitation, and let's keep in touch offline and discuss further.